everyone. Welcome. My name is KATHARINA KANN. I'm an assistant professor at CU Boulder in the US. And today I'm going to talk to you about transfer learning for NLP. Let's get started. To motivate why we might be interested in transfer learning, I wanted to show you this slide, which is of course a bit exaggerated. And just talk for a moment about the current status of NLP with respect to language diversity. I think anyone who has seen the proceedings of an NLP conference could confirm that a lot of the current work in NLP is on English. This has a lot of negative effects. For instance, that some people might have access to certain technology, for instance, websites, because they can translate them while others don't, etc. So one problem is that a lot of the systems that are currently being developed require a lot of data. And like these amounts of data that are needed are often not available for a lot of languages, except for maybe a few like English or maybe Chinese, etc. So as I've said, this is of course a problem in part because the models we're developing pretty much assume that we have huge amounts of data available. In particular, deep learning models, which define the state of the art for a lot of NLP tasks, require a lot of training data. Data can be limited for a variety of reasons, not only that a language is spoken by fewer people, but this is one and an important reason. So data can be limited for languages. Data can be limited for tasks. So depending on what you want to do, it might not be very easy to obtain data. For instance, if you want to do syntactic parsing, what we've seen in the last lecture, this is a very tricky to annotate task. So generally, it is considered that you need expert annotators for this, and you cannot just ask any speaker of the language, please give me a parse tree for this sentence. Finally, another reason why data can be limited is the domain. So assuming you want to build a system that can read a person's complaints and then decide on which illness is the most likely one this person has. For this, you actually need to get medical records. You cannot just tell any human annotator, for instance, like someone, I don't know, in your class, like, hey, can you produce me some data? Please sit down and tell me some invented symptoms and then tell me which illness you have. This is just not a thing, right? So for certain domains, it might be easier or harder to obtain data than for others. So here I want to show you what the discrepancy in terms of the amount of data available is between languages. For English, we have around 49 million, or when I made this, so this might be a bit outdated, Wikipedia pages. For Chinese, we have about 5 million pages. For Spanish, we might have about 5 million pages. For German, we might have around 5 million pages. But Norwegian only has 1 million pages, Afrikaans has only around 200K pages. And then there are a lot of languages that are not present in Wikipedia at all. In fact, the vast majority of languages. Wikipedia only has like some 100 languages. So what does this mean for us? This means for us that NLP systems cannot just be trained for Afrikaans as they can for English, simply because we don't have the same resources. So some approaches that might be very, very well performing for English might not work the same way for Afrikaans. So something we can use in cases where data is limited is transfer learning. So this is called like that because it describes what it is. So what we want to do is we want to transfer knowledge across tasks, languages, or domains. For instance, use some data we have in English to perform a task in Afrikaans, or maybe Indonesian. And we can try to do the same with tasks and domains. So we might, for instance, use data for natural language inference to improve a question answering system. The idea behind transfer learning is that different sources complement and inform each other. And overall, this should reduce the amount of data required for certain languages, tasks, and domains. And in fact, transfer learning has led to very important improvements in NLP over the last years. We've seen this on the timeline, especially from like 2018 on. Semi-supervised learning, which is some form of transfer learning, has really helped for a lot of NLP tasks. Here we can see something. I think I took the screenshot about a year ago or so. But this is a leaderboard for like a public benchmark called SuperGLUE, consisting of low-resource NLP tasks. And this shows the score, like the first line is the score of humans. So humans performed the task, like a subset of it, and then obtained a score, and the score of humans was 89.8. And then all the other ones from like line 2 on are deep learning systems based on transfer learning. And we can see that the second best system is at 84.6 score. So the difference here to humans is really, really small. That's the first important observation. The second important observation is that, well, actually not all of them, but like most of them are based on transfer learning, in particular the first, second, third system, etc., like some of the others. But yeah, so first, transfer learning has led to very important improvements. And second, for a lot of tasks, we nearly reach human performance now using transfer learning. This is our timeline for today. First, we're going to talk about pre-training, which includes some things you might have heard of, like word embeddings or BERT. Then we're going to talk about model adaptation, which is what you do after pre-training. Then we're going to discuss multitask training, and finally, cross-lingual transfer. Let's start with pre-training. So the idea of pre-training is to train a model on large amounts of data from a source task which is different from the target task. And then we hope that the learned knowledge will be useful for the target task, even though we didn't learn it directly from this task. And the reason why we hope this is that we expect that general properties of language can even be learned from raw text or unrelated annotations. So here the entire idea is you have some source task and you want to leverage anything you can learn from the source task to improve on a target task. In theory, any task can be used for pre-training. However, there are some examples that are more popular than others. One is language modeling, which we've seen in the Deep Learning for NLP lecture. And this basically consists of assigning a probability to the next word given a previous sequence. So for instance, here we would want to know which word is likely to follow to the cat sat. Could be down, could be on, could be etc., right? Then a second task, which is kind of popular, is a copy task. So here the idea is encode a sentence and then decode it again. So basically like an autoencoder. And another task that has been used is natural language inference. So here you're given two sentences and you should decide on the relationship between the two sentences. In this example, the first sentence is the cat sat on the mat, and the second sentence is an animal sat on the mat. Since every cat is an animal, the second sentence follows from the first. So now you could ask, why do we choose the tasks we choose for pre-training? And to be honest, one of the biggest reasons is many source tasks are chosen because a lot of data is available. This is kind of obvious for language modeling or autoencoding, because you just need unlabeled data, so you could use everything from Wikipedia. For natural language inference, there have been huge data collections. So this is why we have relatively large natural language inference data sets. So they have been used also quite a lot in English. Okay, so let's talk about the probably most popular example for pre-training, word embeddings. Remember that in our deep learning for NLP lecture, we just assumed we have some vectors that represent words. So now we're going to learn how we could potentially obtain those vectors. And the entire idea of word embeddings is based on this concept that is expressed by those two quotes. One is Firth, 1957, "You shall know a word by the company it keeps." And then there's another statement by Harris, 1954, "Distributional statements can cover all of the material of a language without requiring support from other types of information." So the idea is basically you can know the meaning of a word that you don't know only from the context. So if you ever encountered a word you don't know while reading, I don't know, an article or a book, you kind of know what this means. However, we're still going to look at an example just to make it absolutely clear. So imagine you want to figure out the meaning of word. And here we have the first sentence, which is, "The word is a small carnivorous mammal." So now think a bit about what you think word could potentially be. And then we're going to look at a second sentence. "The word is a predator that is most active at dawn and dusk." Now what you should do is refine your hypothesis. So what is word potentially? And now we're going to look at a third sentence. As of 2017, the domestic word was the second most popular pet in the United States by number of pets owned. And I think now, taking all of those three sentences into account, I think it would be relatively easy to guess that word is supposed to be cat. And this is how this works. This is the entire idea, and you've just seen that in fact it is possible to guess the meaning of a word from its context. So yeah, basically the general idea of word embeddings is that we want to combine the distribution hypothesis with the idea of vectors to represent words. So we want to use the fact that we can guess a word from context to construct word vectors. One possible way of doing so is to create something called a word document matrix. So here you mark in which documents each word appears. So for instance, against appears in document 4, in document 7, in document 8, in document 9, 1, 3, 2, and 3 times. And the same basically for the other combinations of words and documents. Now you can do this for all words. And then we would assume that words that have a lot of overlap in which documents they appear in are potentially more similar than words that don't. So we could use this vector consisting of the entries for documents 1 to 10 as a 10-dimensional word embedding. Another way of doing this is a word-word co-occurrence matrix. So this is a bit closer to the word where the company keeps citations. And Here we do the same. We looked at for documents, for words. So we can say if against and against appear together, well, this is kind of trivial. So they always appear together. But then if against and age appear together, we count +1 for the respective entry in the word-word co-occurrence matrix, and then against and age and etc. And then naturally words that appear with similar neighbors are going to look similar. And yeah, so this leads to things like, for example, hot and cold are usually very similar because they all, like, they usually interchangeably if you don't care about the semantics. You could say, my cup of coffee is hot or warm. You could say, my cup of coffee is cold. And this is actually one of the problems for word embeddings because antonyms usually have very similar embeddings. But yeah, this is kind of the idea this is based on. Let's have one example how we fill out this matrix. So assume we want to learn word embeddings just from this sentence, Betty has brown hair and John has black hair. Then we look at Betty and we decide that we only look as context on one word to the left and one word to the right. So we use a window size of 1. And then we count +1 for Betty and we count +1 for has, because Betty co-occurs here with has. Then for has, we count +1 for Betty, we count +1 for has, we count +1 for brown. Similarly for brown, we count +1 for has, +1 for brown, and +1 for hair. Then for hair, we count +1 for brown, +1 for hair, +1 for and. For John, the same, we count +1 for hair, +1 for and +1 for John. Then for John, we count +1 for and, +1 for John, and +1 for has. So this is now the second time we see the word has. Then for has, we count here +1 for has like itself. We count +1 for John, we count +1 for black on the right. For black, we count +1 for has, +1 for black, and +1 for hair. And for hair, we count +1 for black and +1 for hair. Note that I ignored the punctuation here. So now we could just fill everything else with zeros, and we end up having our word embeddings. In this case, because the matrix is symmetric, it wouldn't matter if you choose the columns or the rows as your embeddings. So now we looked at one word to the left, one word to the right. However, for word embeddings, you can define co-occurrence or the context however you want. So again, it might make sense to explore different options and see which one gets you best results on the development set or validation set. So we can use documents as the context. We can use sentences as the context. We can use tweets as the context, or we can use windows as we just did with like different sizes. And one general rule is that smaller contexts lead to more focus on syntax, while larger contexts lead to more focus on semantics. So this is something to keep in mind. Now, of course, something people are interested in for a lot of reasons, actually besides just application in neural networks, is to measure the similarity of word embeddings. So having a vector representing word A and a vector representing word B, we want to know how similar word A and word B are. On this slide, we have the embeddings we just created. And now let's consider we want to know how similar are brown and black, and how similar are brown and. So we could, of course, just look at the vectors and say like, okay, brown has a 1 for has and a 1 for hair, black also has a 1 for has and a 1 for hair. In contrast, and only has a 1 for hair, and then they differ. So we could assume brown and black are more similar than brown and, but clearly those are vectors. We can just compare them with tools we already know. Here in this example, we're going to look at something a bit shorter. So we have vectors for words A, B, and C, and we can, for simplicity, assume this is showing how many times they appeared in document X and in document Y. So these are the vectors for A, B, and C plotted in a two-dimensional space. And we can see very clearly that apparently B and C are closer than A and B, or respectively A and C. And because those are vectors, we can just compute the Euclidean distance between each pair of vectors. This is the formula, so it's just the square root, basically of this sum. And here are the values you would get for the Euclidean distance between A and B, which is 13.6, and the Euclidean distance between B and C, which is 6.4. So we see that indeed A and B are farther away from each other than B and C. However, now we might want to not take into account the length of the vectors, because what we assume is that potentially A and B should be more similar because they both show up more times in document Y than they show up in document X, as opposed to C, which shows up more times in document X and than in document Y. So what we can do is we can normalize those vectors in order to give less weight to the frequency of each of the words. If we do this, we can plot the vectors like this. So now we see that the normalized vectors look a bit different from the non-normalized ones. In particular, A and B are now more similar than B and C, which is what we would expect if you just look at the relative frequencies in the two documents. Something else that is actually more frequently used than Euclidean distance is cosine distance. You can see the formula here in this box on top. And the important part is that the cosine distance is independent of the actual length of the vectors. So on the left we see the original vectors, on the right we see the normalized vectors. And as is shown, the distance between A and B is in both cases 0.008, while the distance between B and C is in both cases 0.065. So how do you pick a distance metric? Well, usually I would say just go with what earlier work did. But yeah, so basically the other thing would be think about if you want to normalize, if you want to take frequency into account, if you don't want to. But for our original example, are A and B closer than B and C? This is not the case for Euclidean distance, but it is the case for cosine distance. So in many situations, it just makes sense to use the cosine distance, which is why it's de facto the standard. Okay, so there is actually another way of producing word embeddings. Well, there are some ways of producing word embeddings, but probably the most famous one is a toolkit called Word2Vec. And this is based on the same idea as the word embeddings we just looked at, but it is way more efficient. So you can train word embeddings at a high quality really fast using Word2Vec. There are two different training objectives in Word2Vec. One is SIBO, which consists of you given the context and you're supposed to kind of guess the word that belongs in the middle of this context. So you can see this here. So in this example, the word, like 2 words to the left and 2 words to the right are given, and then a neural network is supposed to predict which word is the one that belongs in the middle. And skipgram is doing the opposite. So given a word, a neural network is used to predict the context to the left and the context to the right. So now, having word embeddings, we have exactly one representation per word. Here in this example, it might be necessary to ignore capitalization, but the idea is we have the first sentence, Apple will release a new iPhone in September, and the second sentence, does Apple tastes better than it looks? And I think it is obvious to everyone that the apple in the first sentence and the apple in the second sentence are not the same. In fact, the apple in the first sentence refers to the company, and the apple in the second sentence refers to a fruit. However, using the word embeddings in like their default way, we would have one embedding for both of those, which is not always ideal. So something that has been invented some years ago, probably roughly in the middle between the original word embeddings and now, are contextualized word embeddings. So here the important part is basically just the right one, Elmo, and the idea here is that each word is represented as a function of its context directly. So yeah, this is something that has been used quite extensively for about a year before some even newer methods came up that increased performance even more. And we're going to look at those approaches, known as language representation models, or BERT and similar, like Roberta, Albert, etc. But before we do so, we need to understand the model architecture. And this is the one architecture that's pretty important in NLP, but we left out in the Deep Learning for NLP lecture. This is the transformer architecture. The transformer architecture is largely based on the idea of attention, with which we ended the Deep Learning for NLP lecture. And the idea is you want to compute how important each input is for a given output. And like attention corresponds to an automatically computed weight for each input and each time step in sequence-to-sequence models. And yeah, in fact, we have seen this for sequence-to-sequence models already. Yeah, this is what we had seen, like this little graphic of the model and the performance, and we have seen that this helps for longer sequences, etc. We have also seen this, so yeah, in fact, this is a new example, but the idea is that you can see pretty well this like correspondence between inputs and outputs in terms of which inputs are relevant. So now, based on this idea of attention, Vaswani et al. Published a new model in 2017. And what they tried to solve was that the RNN sequence-to-sequence architecture, so the one we have seen for machine translation, is not parallelizable. And I want to give you some seconds to think about why this is the case. So the RNN sequence-to-sequence architecture is not parallelizable because each new output or each basically computation depends on the previous computations. So we always need to go from left to right, or at least like in some order, but we cannot compute everything at the same time because we cannot compute something that depends on something that we haven't computed yet. So they suggested a solution for this, which they called a transformer architecture, which is in fact parallelizable, so it can reach state-of-the-art performance quicker than the corresponding RNN sequence-to-sequence architecture. And this is how this looks roughly. So we have, like for this sequence-to-sequence version of this, we still have an encoder and a decoder. And the encoder here consists of n equals 6, so 6 layers. And each of those layers consists of 2 sublayers. So what is shown here in yellow, basically the upper, the upper box is just one of the 6 layers. So you can see there are 2 sublayers. One is the self-attention, denoted here as multi-head attention, and one is a feed-forward network. And the inputs are the current embedding and the position embedding. So now, because we don't have the recurrence, we need to somehow signal to the network, this is the input at position 2 in the sequence, for instance, or this is the input at position 6. So this is where the position embedding comes in. But then basically everything is attention to all positions in the encoder and a feed-forward network. So no recurrence anymore. The decoder is very similar to the encoder. Here in this case, it consists of n equals 6 layers, but note that this is a hyperparameter that can be tuned with your development or validation set. Just in the original paper, it was 6 layers. Besides that, the decoder consists of 3 sublayers. So 2 of them are the same as for the encoder. We have a self-attention layer, we have a feed-forward network, but now we also have encoder-decoder attention, which is this connection that we discussed in the last lecture that you need between the encoder and the decoder. And yeah, similar to the encoder, we now have as inputs the current embeddings and the position embedding. The good thing is training now can be done in parallel for all output positions. And what do we do about testing? Well, it's a bit trickier because if you actually want to generate a sequence, you still need to generate in some order. So usually testing is not parallel. Yeah, here are some performances. So BLUE is the most popular machine translation evaluation score. The higher, the better. And then we have the training cost, so the lower, the better. And we can see here that the transformer, once in the base model, once in big, so basically all the hyperparameters are larger. So both of them outperform all other models in translation from English to German. The bigger transformer performs better. Oh yeah, so these are the ones I'm talking about. But then we can also see that additionally, the training cost is the lowest for the small transformer. So, I mean, this is kind of why this became so important, because it, on the one hand, it improved performance, and on the other hand, it was also cheaper than existing models. So now we can look at the language representation models that make use of the transformer architecture. And I titled this BERT and Co because a lot of people decided it was funny to name their models like BERT, which is why we have Roberta, Come on BERT, Shoe BERT, Albert, etc. So this is all still in our overall area of pre-training, and you're going to see very soon why. We have a transformer model here, just the encoder part, that is used to read sentences and then do something with them. In particular for pre-training, we do something that is kind of like language modeling, but not really language modeling. So what we do is the input is something called a masked sentence A, masked sentence B. And masked sentence just means that some of the words are blanked out. And then the goal is to predict the masked words. And besides that, the original BERT came with an additional pre-training objective, which has later on been shown to not be actually helpful, which is next sentence prediction. So you're also supposed to predict sentence B from sentence A. So the model is trained on this, which doesn't need any annotations, right? You just take raw text, you mask words, and you predict the words. So this is like something that can be easily done on basically a lot of data, because we do, for a lot of languages, have a lot of unlabeled data available. And the idea of BERT is that after you do this pre-training, you then do fine-tuning. Fine-tuning of the pre-trained model. Okay, so people might have heard about OpenAI, And it's the same basic idea, but there are many small differences, including 2 unlabeled data tasks in place of language modeling, and neither requires predicting the future. So we can use an encoder style transformer rather than decoder style, and it's a very big model. So we've seen before that the originally introduced model had about 6 layers. So now our model has 24 layers, and this is more than 300 million parameters. Remember our model from last lecture that had like, I don't know, maybe I think it was like 22 parameters. So this is definitely a really, really big model. So yeah, we're going to discuss this a bit more in, actually not this one, but in general, the adaptation in the next part of this lecture. But what you need to know now is that for downstream tasks, we take off the last layer of the pre-trained model, add an additional classification layer, and yeah, then we train that model on task-specific data. And on top of what exactly we add, this like task-specific output layer depends on the task. And we can see here why. So assuming we have BERT and we want to do a question answering task for which we want to label a span in text, then we need to predict something like start and end span. If we want to do single sentence tagging tasks, we need to predict one label for each sentence. So we need to have one output over each of the inputs. If you want to make a sentence pair classification task, then usually this is one prediction on top of like an end of sentence symbol, position, encoding, something like, okay, let me try to explain this better. So we have the end of sentence symbol, as we've seen before, but this, of course, now also has a representation, and the class label is usually predicted on top of that one. And yeah, we can do this for sentence pair classification. We can also do this for single sentence classification. So you do have basically something like all the hidden states as we've seen before for the RNN, but you can choose to predict on only some of them. You can choose to predict on the last of them, or like first, but like the end of sequence symbol, or you can choose to predict on all of them. Okay, let's have a quick look on what methods actually work. So here we can see the GLUE score. GLUE is another benchmark similar to SuperGLUE, but less focus on low resource tasks. We can see that glove bag of words, so using basically word embeddings and a bag of word approach, as we've seen before, we reach a score of 58.9. Then using a better single task model could give you around 66.2, etc. But the really important one is the Elmo one, which received some gains over the previous ones just by using contextualized word embeddings. Then we had another pre-training approach, which gave us 72.8 as a score, but then using BERT gave us 80.4. So this is why BERT became that important. Like it just showed amazing improvements on a lot of tasks. And why? Mostly because it's just a really big model which has been trained on a lot of data. So after BERT, there were several like follow-up improved versions of BERT. And I think they're still kind of coming out, so keep an eye out for that. And always make sure that if you want to work on NLP, you know the state of the art for your task, you know what is the model that currently works best. So next we're going to talk about how we can adapt pre-trained models to tasks. So when do we want to do this process, which is also known as fine-tuning? First, when the target task is different from the source task. Second, when the target domain is different from the source domain, domain adaptation. And third, when the target language is different from the source language. So in general, you always want to do this if your final in-task training data is different from something the model has been trained on before. And as we will see, this can contain only parts of the model or concern only parts of the model as well. For instance, you can think about which parameters should be updated, how about unfreezing, etc. So the first thing you want to know is which parameters are actually shared between the pre-training and the fine-tuning task. In the case of word embeddings, we can see this as only the very first layer, so the embedding layer of a neural network being shared between some source task, potentially, the word embedding training, and the target task, which can be any other task. And there are other options though. So for BERT, for instance, nearly the entire model is shared, everything except the output layer. And you can update as much of the model as you want later on. Here in this case, we have as an example a bidirectional RNN, which has word embeddings as input and also a representation of the word on the character level, which is obtained by character level RNN. So technically what exactly this model is not very important. The important part is here's an output layer which predicts parts of speech, so pronoun, auxiliary, verb, and we could now substitute this layer by something else. So for instance, by named entity recognition output layer, in which case we don't want to get a probability over a possible part of speech tags, but over BIO tags. So here we have OOO for none of those being a named entity. Yeah, and in this case, you could think about if you actually want to update the entire network, or if you only want to update the output layer, or maybe you want to update all parameters except for the character level RNN. So this is totally up to you. And again, you should try what works best depending on your task. So another option, the unfreezing part, is that you first you don't train some of the parameters and then they gradually start training them. And yeah, basically those are word embeddings, as I've already said. Then the other thing you can think about is the training regime. So for instance, the parameters you want to update, like what is the learning rate you use? Do you want to update rather radically or maybe only in very small steps? And then for how many epochs do you want to update? So this is a little bit of trade-off of between not adapting the model fully to the task if you use too few epochs, or maybe overfitting a very small task-specific training set if you train for too many epochs. In particular, target tasks for this like pre-training adaptation approach, pre-training fine-tuning, are very often tasks with small training sets. So this makes the overfitting that I just mentioned, of course, much more likely. In most cases, except for very general models like BERT, the pre-training, so the source task and the target task, are somehow related, or at least if they are related, usually results are supposed to be better. So this is kind of due to the fact that whatever is a task, like actually here I usually use task as a synonym for dataset, is a very unclear question. For instance, you could say that a certain like data set is another task than another data set because it's focused on another domain. But then maybe some sentences actually are domain independent, so they could belong to both. So there's like a very unclear distinction between different tasks in general, which means that the closer the tasks are related, the more they could actually be the same task, so the more helpful they are. And yeah, SuperGLUE has recently been a popular benchmark. Now there have been some newer ones very, very recently, like Extreme for cross-lingual transfer. But yeah, So this is more or less what you need to know about the target tasks for fine-tuning adaptation. Some more words on SuperGLUE, also because it's from the group I did my postdoc in. So this is, yeah, a fairly nice benchmark containing a collection of data sets. One is bool Q, which contains yes/no questions. One is WSC, word in context. So this means roughly word sense disambiguation. So what does this word in this context mean? And then we have RTE, recognizing textual entailment, which is very, very similar. So there you could easily argue they could basically be the same task to natural language inference, just that instead of having 3 labels, entailment, contradiction, and neutral, we only have 2 labels, entailment or no entailment. Yeah, and there's a set of other tasks. So if you are interested in working on NLP and you have not so much experience yet, you might want to check this out. It's a very good starting point. The next thing I wanted to discuss with you is multitask training. So what we've done so far is that we did pre-training on one task and then adaptation to another, ideally related but potentially unrelated task. Multitask training doesn't do this 2-stage setup. Instead, we train on the source task and the target task at the same time. So yeah, as I said, again, we have main task data, we have auxiliary task data, which kind of corresponds to the idea of the target task as the main task and the source task as the auxiliary task. And then we need to first decide which model parameters to share. So this is about the same as for pre-training and adaptation. You have the exact same design choices. So you could share everything from the entire model until only the attention mechanism or only the word embeddings, etc. And then what you do is you train the model on both data sets together. So basically, you compute the loss for examples from one data set from the other, and then you do updates taking both types of losses into account, and you can potentially weight them. So if you want your main task, your target task to be more important, you can give it more weight. Yeah, and this summarizes this entire idea. So multitask training refers to using 2 tasks at the same time, while pre-training and fine-tuning or adaptation refers to training on one task after training on the other task. Yeah, I think this is basically what I just said. So you should think about which parameters you want to share, and you should figure out how you want to weight your losses. The easiest would just be to weight them equally. And then potentially you can also upsample, downsample your data. So for instance, if one task has a lot of training data and one task has very few examples, you might want to upsample the one with fewer examples. Yeah, and now this here, the 2 times, means that now instead of having one output layer, then discarding it and then using another output layer, you use both output layers simultaneously depending on the input example. So one thing that is maybe important, because I heard that many people got confused there, is that you don't actually need to have both annotations for all your examples. Meaning, if you want to do this like part of speech tagging and named entity recognition, you don't need to have the annotation for part of speech tags and named entity recognition for the same sentence. You can have sentences that only have part of speech annotations and sentences which only have named entity recognition labels. But then, depending on which example is used as input, you need to basically use the respective output layer at the time to compute the loss for training or to compute your output at application time. Yeah, again, as for the pre-training adaptation paradigm, usually target tasks are tasks with small training sets that are somehow related to a source task, but not necessarily. And yeah, this is basically because this entire transfer learning idea, as I motivated in the beginning, is based on the assumption that we cannot learn everything that we theoretically could learn from the examples we have because we don't have enough of them. Yeah, so this is the same as for pre-training and adaptation. So then one question people have been very interested in discovering, actually both for pre-training and fine-tuning and for multitask training, is which source tasks or auxiliary tasks work well for which target tasks. Here's a study from 2017, and it shows the improvement or loss of performance from combination of different main and auxiliary tasks. And we can see, most importantly, that the results are pretty much mixed. So yeah, this is a set of a lot of for the time tasks. And it is tricky, so it seems that multi-word expression detection seems to be always in the red, so like in the positive area. But overall, they're negative results, they're positive results, and that doesn't seem to be too clear of a picture. And in fact, this is still very much an empirical question. Some of the things that the authors of the study found was multitask gains are more likely for target tasks that quickly plateau, with the non-plateauing auxiliary tasks. Tasks with vocabulary overlap help more, closely related tasks help more, so the last part is probably not very surprising. But yeah, overall this wasn't very conclusive, and a lot of people are working on this now to see how to use labeled data for pre-training besides the BERT approach, which is using unlabeled data. But it is very tricky to figure out what exactly a model learns from certain source tasks for certain target tasks. Something else you could ask is, how about a combination of pre-training and multitask training? And good news, all combinations are possible. And in fact, if the target task training set is small, fine-tuning on this set alone might lead to overfitting quite easily. So it might be a good approach to do multitask training while doing fine-tuning on the target task. But yeah, so you can definitely do pre-training on multiple tasks. You can do pre-training, multitask, fine-tuning, etc. So yeah, all of this is totally reasonable and might help. And as I like to emphasize all the time, ideally, if you are unsure if something is a good idea or a bad idea, you should try it out using the development set. And the next thing we will discuss is something called cross-lingual transfer. The idea of using information you have available in a high-resource language to somehow solve a task in a low-resource language isn't new. In fact, there are some very trivial ways of doing this. Well, trivial. But yeah, one is to translate training data from a high-resource language into a low-resource language. So let's assume you want to do summarization in Indonesian, but you don't have any training data, but you do have training data in English. Then something you could consider doing would be to translate the English training data into Indonesian. And then you can use this data to train your system and then apply it to whatever you want to apply it to. The other option is to translate test data from a low-resource language into a high-resource language, or this could in fact be like the real data you're interested in. So again, assuming you have some, Indonesian articles you want to summarize, you could translate them to English, then have them be summarized by your summarization system and translate them back. Another option to do cross-lingual transfer are multilingual embeddings. So this is based on the idea, this is not so easy maybe for text generation, but for something like classification, so maybe like I don't know, a sentiment analysis, that you could present everything in one big space so that the word embeddings for maybe something like dog in English are very similar to the word embeddings for dog in Indonesian, so that for a system, they basically look the same. And then you can just use the same system for input in either language, and it would just work the same way. And something else that you can do is multitask training for cross-lingual transfer. So you can train a system, maybe based on multilingual embeddings, on tasks in a high resource language and tasks in a low resource language at the same time. Now let's look at this in a bit more detail. So the translation of data seems in theory like a really good idea, but first of all, you need very good machine translation systems for this. And to build those is not really doable for many low resource languages either. And using bad machine translation systems leads to a propagation of errors. So in general, this can end up with a very poorly performing result. Cross-lingual embeddings, in turn, do not need a machine translation system. And there are quite a few options to obtain embeddings in the same space. We're not going to cover them here. But yeah, you can easily search for this on Google Scholar if you're interested. But the main idea is what I said before, that the final system is basically language agnostic, and it doesn't care if your input in actual like text form is English or Indonesian. So this is an easier to obtain option than the translation of training or test data. And if you want to do multitask training for cross-lingual transfer, you're faced with the same decisions that you need to also make for, yeah, basically not cross-lingual, like monolingual multitask training. So you need to think about which parameters you want to share, first of all. And you need to think about how you want to weight losses. You need to think about if you upsample, downsample your data. So the idea of multitask training for cross-lingual transfer is that you treat each language as its own task. So this means in practice that instead of saying maybe part of speech tagging is one task, morphological tagging is the other task, you would say part of speech tagging in English is one task and part of speech tagging in Indonesian is another task, and then you just do multitask training. One thing that you can consider doing both for multitask training and for like cross-lingual transfer via multitask training is to use a task embedding, which in the case of languages translates to language embedding. This has been done for a large set of tasks. For instance, famously for machine translation, Johnson et al. In 2017 presented the system that was trained on like translating between many languages, like not simultaneously, but like it was trained on all of those languages simultaneously and then translates only for one. And the idea here was that you give the system an embedding showing what language it was supposed to translate to. So if your original training data was how are you and the target side was como estás, then this should be modified to the lower part, so 2ES as in like 2, right? Like not necessarily the number, 2ES for Spanish, how are you? And the output should be como estás. And this was actually quite an interesting paper because the authors, besides other things, showed that this made it possible to produce mixtures by mixing the language embedding. So you could produce a sentence that's like half Korean, half Spanish or similar. So yeah, it's kind of like a game, right? It's not really very useful, but it was kind of cool to see. To conclude this lecture, I would like to talk to you a little bit about my own work on transfer learning for morphological inflection. You will probably be able to see a lot of the things we have just discussed, so this is kind of nice to show you how this can be used in practice. First, let me tell you quickly what morphology is. Morphology is the study of the internal structure of words. It's concerned with how words can be composed out of the smallest meaning-bearing units in a language, which are also called morphemes, and also how words can be decomposed into those units. To give you an example, we here have the English word wash. This is already its own morpheme, so you cannot meaningfully decompose this. What we can do then is we can append a suffix, the suffix ed, and we end up with a past tense form of the verb wash, so washed. Something else we can do is we can build a compound by prepending brain. So here we end up with the word brainwashed. And why is it useful to teach NLP systems about morphology? Well, because, for instance, if you don't know what wash means, but you know the meaning of brain and you know the meaning of like the suffix ed, you can still conclude that potentially you have a verb here in the past tense form and that something is happening to a brain. So this is clearly much better than just assuming the entire brainwashed word is an unknown word and not having any information. The canonical form of a word, which is the form we can find in a dictionary, is called the lemma. So here we have the paradigm, which is the set of all inflected forms of the lemma eat. In English, verbs commonly have 5 different forms. Here, in this case, we have the forms eat, eats, eating, ate, and eaten. Now, a common task in morphology is morphological inflection. This task consists of given the lemma together with a tag or like a morphological tag indicating which form we want to have to generate this indicated form. In this example, given eat and present participle, we would want a system to generate the word eating. The reverse task is lemmatization. So this consists of given an inflected form producing the lemma of this given inflected form. This can in fact be quite challenging for different reasons. One is that in many languages we have different inflectional classes. For instance, in German, the nominative plural form of Mund is Münder, but then the nominative plural form of Hund, which is very similar to Mund, is Hunde and not Hünder. In some languages we find stem changes. For instance, in Spanish, the first person singular present tense form of aburrir is aburro, but then the first person singular present tense of dormir is duermo and not dormo. So we can see that here this O got changed into U and E. And something else we have is irregular inflections. So we all know that the past tense in English is usually built by appending ed. So here the past tense of walk is walked, but the past tense of eat is not eated, but ate. And then there are even more irregular inflections, like the past tense of go, which is went. So the first research question that I was working on actually in my PhD in 2016 was how can we model this task of morphological inflection? And what my advisor and I did was we cast this task as a character-based sequence-to-sequence task. And we used an attention-based encoder-decoder network as proposed by Badenow et al. 2015. So this is exactly the model we have seen at the end of the Deep Learning for NLP lecture for machine translation. However, we changed hyperparameters and made it a little bit smaller. And then the idea was that you can apply it to this sequence of features. So first here, we encode the feature of the input form, and then we encode the 2 features or tags describing the output form, present participle. And since, as I said before, this is character-based, we encode each character as its own input element. So the input here is EAT, not one input EAT. And the output that we want to generate is, again, a sequence of characters. So here it is EATING. Yeah, why do we need those features? Simply because otherwise this task is kind of ill-defined in the sense that the network doesn't know if it should produce ate, eats, eating, etc. So yeah, this is the network. We've actually seen this before. So we have an input embedding layer using characters and tags, tag embeddings. Then we have a bidirectional gated recurrent unit, a GRU, where the hidden states are representation of the input in context. We have an attention mechanism which computes a relevant combination of the encoder hidden states at each time step. And we have a decoder, which is a unidirectional GRU and produces the output characters. And a target embedding layer, which embeds the last predicted character. But so what I said before about the tags that we need is basically the part that enables multitask training, because you do have another option. You have an option to produce like one network for the third person singular present tense, one network for the present participle, etc. Right? So you can basically, for each possible output slot or output form in your paradigm, have a separate model. However, by encoding tags, this is kind of like the same as what we've seen for machine translation in 2017, so 1 year later, where the languages were like separate tags. So yeah, we basically encode these tags to be able to train the model on all data at once, doing multitask training, sharing all available parameters. And yeah, humans also do this, right? We kind of like learn from related tasks that we already know. We performed an experiment to verify that the multitask training was an effective approach. And for doing so, we designed a setup where we had 1,000 examples for 3 source tasks. So this means basically 3 mappings of one paradigm slot to another. And then we had a varying number of examples for the target task. And here we can see that the purple line is our approach where we do multitask training. And this is the performance, the accuracy only on the one task that we reduce the data for. And then we have the blue line, which is training a model exclusively on this one task, so not doing transfer learning. And we can see that for settings where we have only a few examples, like the very right one, the performance difference between doing multitask training and not doing multitask training is huge. So this clearly confirms that there are a lot of cases where this can be very effective. In order to give you an idea, the very right point uses only 36 training examples of the target task. Yeah, this system performed in a shared task, but this is also just to confirm that, that multitask training is really effective. So here we have the one LMU, which was where I did my PhD, which achieved 95.56% accuracy on average, and all others were like at least 10% lower. So then I also wanted to answer another research question, which was, does cross-lingual transfer work for morphological inflection? This was worked together with Ryan Cottrell and Henrik Schütze in 2017. So we have seen this, that we can do different things to obtain cross-lingual transfer, for instance, translating of the training data, translating of the test data, or using multilingual embeddings. However, there's one problem with this, which is that all of this is based on the idea that the meaning that you want to express is still the same, independent, so basically independent of the language, so you can't just translate. This is not the case for morphological inflection. Like by translating a word, I would not expect you to magically end up with the right inflected form. So the question is, why would we expect cross-lingual transfer to help for morphological inflection? And for this, I have a small a thought experiment, which is actually much nicer in person, but I still want to encourage you to participate. So let's assume, or just imagine you're a neural network or any sort of machine learning system, and you're given this example. So plural and CAT maps to CATS. Now you're supposed to update your parameters to train yourself on this one example. And after this training is complete, you are supposed to solve this example. Plural of DOG maps to which output? And I all encourage you to make a guess for you privately. And I would assume a lot of you guessed that it would be dogs, but in fact the answer that the system would probably give is cats. Because looking back at this example, this is the only thing the system has ever seen, right? The system, or you, if you're the system, only knows to produce cats. So of course cats is produced for whatever the input is. But now if we train on all of these examples, we train on plural of CAT, CATS, and then some Spanish examples. So plural of gato is gatos, plural of mano is manos, etc. We are able to learn that appending an S is necessary for the plural, and then potentially we can generate dogs for the input dog. Now, of course, you could say this is based very much on the idea that both English and Spanish append an S for the plural. However, this is also how cross-lingual transfer works. Like there is some information in one language that you can also use for the other. And in fact, we do have a lot of cases where similar languages inflect in similar ways. Here we have the verb lavar, wash, in Spanish and Portuguese. And this is only a subset of all forms, only the present, some of the present tense forms. But we can see that out of those 6 forms, 4 are exactly identical. So we have lavo, lavas, lava, lavamos, and only then we have differences. So if we assume we just do multitask training on all of those together, we share all parameters, we would expect our network to perform perfectly for those 4 afterwards. However, of course, we also want to make a distinction for the last 2. So what we do is we use a language embedding, which is very much in parallel to the feature tag embeddings that we used before, and in parallel to the language embedding for machine translation that we've seen. And then we can just train the overall architecture on all languages at the same time. We don't need to think more about parameter sharing, etc. And we can obtain our results. So we performed experiments trying to answer the following 3 questions. The first one was, is cross-lingual transfer possible for morphological inflection? So I've given you some intuition why I think it should be possible, but of course, we need to confirm this. Then the second question is, how much annotated data do we need in the low resource language? And the third question is, how closely related do source and target language have to be? And here we get the results of our experiments trying Arabic, French, Italian, Catalan, and Portuguese as the source language, so the high resource language, and Spanish as the low resource language. And we can see here, so the blue line is a single task model that is exclusively trained on Spanish. So we can see that for small numbers of examples, we indeed can observe quite a gain from adding this multitask training. What we can also observe is that the lexical similarity, which we kind of use as a proxy for language similarity, is pretty much correlated with the gains we see. So the more similar the languages, the more gains we get. We also tried one-shot results. So this means that we tried to get results for 10 tags, features that we have only seen once during training in Spanish, while using also the data from the source language, we can see that with only one example in Spanish using Portuguese data, we can get up to 44% accuracy. Then finally, I worked together with my advisor on a third research question. What can we do if data from related languages isn't available either? And here we thought about semi-supervised training, so make use of large unlabeled corpora and learn properties of language from general text, so raw text. So how we did this was we didn't do pre-training, which would also be a valuable option, I guess, but we did multitask training with an autoencoding auxiliary task. And we created examples from corpus data and added a task embedding and maximized the joint loss. So this is something, yeah, I haven't discussed this very explicitly how to actually do this, but we basically trained together on all examples, marking in the beginning what the example belongs to. Here, this AE is autoencoding, and then you just encode the word, you decode the word. And we also tried the same for random strings, just to see, yeah, basically where the gains come from, as I will explain now. So why should this help? The first reason why this autoencoding could help is because similar to the language modeling pre-training tasks, it could be useful to just know which characters are frequently following on each other in a language. Oh, that's actually the lower part. So the upper part is about that the encoder-decoder doesn't have an explicit way of knowing which character in the input corresponds to the output. So, so this is very important because for morphological inflection, a huge part of the string is usually identical, right? Like in eat, eating. So yeah, to learn which input maps to which output is very helpful. And then the language modeling. And why we use the random strings is because this shows us the difference between the upper part, which is just the mapping, which can be learned from random strings, and the language modeling on the lower part, which cannot be learned from random strings. Here are the results we obtained. So you can ignore the very left part, I think, but the second one is basically a normal like RNN encoder-decoder model, which obtained like 70.5% on the data we used. And then we used a sequence-to-sequence model and corpus data, which obtained 81.2, and the random strings obtained 80.4. So we can see that a lot of the gains potentially come from the copying, and only a small part of the gains comes from the language modeling, but there is a gain. Okay, I think that's it with the presentation of my own work and also overall with this transfer learning lecture. I wanted to point out something to you, which is that work is pretty much needed for low resource languages. I think any one of you who already has worked on NLP knows this. And there are a lot of open areas, so you could check if one of those interests you. So one area is learning from limited resources. So we need efficient machine learning models and data augmentation approaches. Then for low resource languages, often it can be helpful to do language-dependent pre-processing, like word segmentation, morphological inflection, and analysis. So if you're interested in that, feel free to contact me. I'm always interested in talking about morphology. Then something that is kind of less attractive in NLP is that we need data sets. So we need to adapt existing data sets to new languages, create new data sets for known tasks in new languages, and create data sets for language-specific tasks. And finally, we need work on transfer learning, so knowledge transfer. We need work on multitask learning or training, cross-lingual transfer, domain adaptation, and pre-training.